Okay, before getting to Verilog, let's first check the design flow. Design flow for IP design and IC design. First, let's check design flow for IP design. The first step is you have to understand the design requirement. That is, the function of the block, the performance of the block, and you will use which platform to implement the block. For example, if you want to design an AI accelerator, first you have to study the algorithms used in the AI networks, such as algorithms in RESLate, algorithms in GoogleLate, and algorithms in other networks. Then you have to define the performance of your block. For example, the most important performance for AI accelerator is the AND multiply operation you can provide within a second, such as you define your block to the performance of 500 G operations per second, or 1T operations, or 10T, or even 100T operations per second. Different requirements will result to different hardware architectures. Okay, and then you have to decide which platform will be used. For example, you will implement the function in FPGA, or you will implement in ASIC. And for ASIC, what's the process load you will choose? The 130 nanometer, 14 nanometer, or even 7 nanometer? So you have to decide which process load you will use. Process load has impact on the clock frequency of your design, which in turn affects the performance of the design. Then for next step, you have to go deep in the algorithm. At this step, you may need to build an algorithm model for your function. Maybe you will use C language, or MATLAB, or Python to build the model. This model will be used at the simulation stage. And if the algorithm is rather complex, you may have to read some papers at this stage. And if there is some bus protocol involved in this block, for example, some complex protocol, USB, PCIe. If there is some complex protocol in this block, you have to study the protocol carefully. After that, we are going to the stage of hardware architecture define. In this step, you will try to map your algorithm or the function of the block to hardware architectures. For the AI example, how to map the operations, that is the many loops in the algorithm, to hardware architectures. This is the question, and you have to resolve this question at this step. Typically, you have to define the control flow and data flow for your circuit. That is how data is moving in your circuit and how data is computed when they are moving in your circuit. If the algorithm is rather complex and you feel it's hard to find a good hardware architecture, you may need to read some papers on that topic. For example, you have to search IEEE papers, or you have to search some papers on Google talking about this topic, and you may get some idea from these papers. Then after you have finished that, you have to document it. Document your idea in a file. We call this file the design specification. After you have designed a high-level architecture for this block, you may need to partition it to sub-blocks. For example, if the function is rather complex and you think it's difficult to code it in a single block, you have to partition it. That is, you divide then the complexity of sub-block should be much lower than the one block big design. For example, this is your AI accelerator. Then you may divide it into many sub-blocks. For example, this is the data input. Yes, this is the data output. Then you will do convolution in this block and maybe pooling in this block. Yes, or something like that. So the complexity of each sub-block will be much smaller than the whole design. And what's the guideline to divide a function to sub-blocks? The guideline is the function of each sub-block will be clearly. That is, the cooperation between sub-blocks will be defined clearly, and reducing coping between blocks. The next is you have to divide it into small blocks that you think you can handle. That is, you can think it clearly and code it. Okay, after the divide of sub-blocks, you have to go deep into each block. That is, you have to define the hardware architecture for each block. This is also the data flow and the control flow for this block. And after the define, you have to document it in a file. That is in the design specification for this sub-block. In my opinion, all the steps before this line is the most important steps for the whole design process. They are the planning steps. If you dig it deeper in these steps, you may have a better life in later stages. For example, if you misunderstanding the design requirement, misunderstanding the algorithm, the bus protocol for this block, all the outcomes of the following stage will be wrong. Yes. So these steps are the planning stage, and make sure you are headed the right direction. Okay, after that, we will get into the implementation stage. In this stage, you will use some language to coding your idea, to coding your hardware architecture. For example, you may use Verilog, or VHDL, or system Verilog. And these are the text editors. The next is the IP integration and simulation stage. For IP integration step, you just collect the submodules up to make the whole function block. And for simulation and verification step, you have to build a simulation environment and test the function of your design using this environment. For example, it may be something like this. This is your design. That is design under test. Then you will write some blocks to generate stimulus to it. That is drive the input signal of your design. And also you have to monitor the output of your design and check the function of your DUT. Then report the simulation is pass or fail. So this is the simulation environment. The function is drive input of your block and monitor the output and check the result. And in this step, if you think the function of some of your sub-blocks are rather complex, and you don't have confidence about these blocks, you may choose to do sub-block simulation first. You build a simulation environment just for this sub-block. Then, after the verification of this sub-block, you will integrate it. And this block is supposed to have less bugs after it has been integrated. Okay, after that, we go to the stage of coding check. That is, you use tools to check your RTL code. For example, you use unint, a spyglass, to check your RTL code. These tools will find some potential errors in your RTL code, such as unintentional latch, combination logic loops, or something others. After that, we usually have a design review. The owner of the function block will call for a conference and invite some engineers in your group to review your design. I think this is an important step. In this step, we will double check whether you have understood the algorithm, the bus protocol correctly, and we will check whether your hardware architecture is reasonable, and there may be some advice to improve your hardware architecture. And also we will check whether your verification is complete. That is, you have generated enough stimulus to test the function of the block. So I think for beginner, this is a good step for you to improve. In this step, you can communicate with senior engineers and learn a lot from them. Okay, after this, the design flow will be divided into two threads. The first thread is the ASIC design flow thread, and the second thread is the FPGA emulation thread. For the ASIC thread, we will do design synthesis using EDA tools such as design compiler from Synopsys. Then we will do logic equivalence check. This is also using EDA tools to check whether the synthesized netlist is function equivalent with RTL code. And for FPGA emulation thread, we will synthesize the RTL code using FPGA tools and implement it on FPGA platform. And we will run the design up on real FPGA device. And in this step, we will co-work with the software engineer and realize all the functions. For the AI accelerator example, it may be something like that. This is your PCB board and this is the FPGA chip installed in this PCB. Your AI function will run up on this FPGA device. For example, the function of your AI accelerator is to detect the face of human. So the software team will feed some figures to your accelerator and check the result of your detection. So there is the question, why we need the FPGA emulation process? Why? To my understanding, the first reason is the design can run much faster in FPGA than in simulation tools. For example, it may be 2 times or even 100, 1000, or even 1 million. or 1 million times faster than simulation tools. You can run much more tests, and this will help you to find potential bugs. The second reason is, in this step, we will put the function in real silicon device. Yes, the FPGA device is a real silicon device. And for other steps, such as the simulation step, the simulation is just running in the EDA tools, not in the physical environment. So the FPGA emulation will give you more confidence about your design. That is, if the design can run up in FPGA device, you will have more confidence that the design will run up in ASIC chips. And the third is, the software team will involved in an early stage of the design process. If you don't do FPGA emulation, when the software team can involve in? Yes, they can just involve in after the tape out and when the chip is returned back. So this is rather a very late stage in the whole design process. If your design has been run up in FPGA device, the software team can involve in and the software team can involved in. The software team can involve in an early stage of the design process. So this will shorten the time to market. Okay, if we are lucky and we have passed all the steps, then we are done. We can release the IP block. Okay, that's all for design process for IP design. And this is just a general process. It may vary from company to company. And please note that these are the most important steps in the whole process. Okay, in this slide, I will show you the general design flow for IC design. The first step is marketing requirement. In this step, the marketing team will gather requirements from customers. Then, based on the information of marketing, we will define the function of your chip. For the whole design process, this is the most important step for IC design. I guess all the IC design companies must have such experience. You think you have designed a wonderful chip, but this chip can't be sold out. Nobody needs it. This step is used to make sure you have designed a chip meet the requirements of your customers. The next step is based on the function requirement. You will architect the chip or the SoC. That is, you will define how the software and hardware will co-work, and which bus protocol you will use in the SoC, and you will analyze the bandwidth of the bus and check whether the bandwidth will meet your requirement. And also you will plan for the clocks, reset, and power for your design. Then you must divide the function of the chip into several IP blocks. So you will get into the IP design process and fully verify the function of your IP block. So in this block, you will do the whole process in this slide. You can also buy some IP blocks from IP vendors such as ARM, Synopsys, or Cadence, or some other IP vendors. Then you will integrate the IP blocks to make the function of the chip. And you will do simulation and verification. Also the coding check. Use the link tools such as Spyglass. At this point, the design process will divided into two threads, the FPGA emulation thread and the IC design thread. So the FPGA emulation thread is something similar we have talked here. And for the IC design thread, you will do design review, then synthesize, and you will insert design for test logic in your design. And also maybe clock gating cells. Clock gating is used to saving power. And DFT circuit is used to check whether there is some flaws inside your chip when the chip is manufactured in foundry. So after that, you will use the place and route tools to place and route your design. You will do design rule check on the routed design and extract the gate level netlist, the resistor, the capacitance from the routed design. For these steps, you will do something on your design using EDA tools. So after each step, you will do logic equivalence check on your design to make sure after each process, the function is still equivalent. That is, we will make sure the function of your RTL code at this point will be the same as the function of the design has been placed and routed at this point. After the extraction of gate level netlist and RC values, we will use this to do post-gate simulation and also do LEC check and timing sign-off. For timing sign-off, we will use STA tools to analyze the timing of your design. And if we are lucky, we have passed all the steps, then we can tape out. That is, pass your GDS2 files. To foundry and ask the foundry to manufacture the chip. Then when the chip is returned from the foundry, we will test it. We will assemble the chip on a PCB board and boot it up. That is, make the function of the chip run up. Then we will measure some physical parameters, such as the power consumption of the chip. Okay, suppose we passed the chip test process. Then we will go to the mass production process. Before mass production, you have to design and debug your DFT patterns. Using DFT pattern, we will detect the bad chips returned from foundry and discard them. We just release function-aware chips to our customers. And in the process of mass production, you have to continuously improve the PPM and yield for your chip. So what is PPM? That is part per million. For example, if we delivered 1 mini chip to our customers, and even we have used DFT patterns to detect the bad chips, but there is still some malfunction chip delivered to our customers. For example, maybe 100 per million. So in this case, the PPM number should be 100 PPM. And this may make our customer not happy. And we have to minimize this number. For example, maybe minimize it to 20. That is, there is just only 20 malfunction chips within 1 million delivered chips. So this time, our customer may happy with this ppm number. And for yield, the design house will co-work with foundry to improve the yield. If there is 100 chips returned from foundry and after the DFT test, there is just 85 chips can work well. The yield is 85%. And the design house may co-work with foundry to improve this number. For example, we want to improve it to 90%. The bigger for this number, the more profit we will get from this project. Okay, that's all for the IP and the IC design flow. Thank you.